In problem 12.57, we have a metal bracket attached to the wall by a screw, which provides enough force to keep this thing from slipping and also to keep it from rotating. And we're asked to find this force right here, given that here's the center of mass of the bracket that extends out this way at a distance of r sub m. The weight of that bracket is m, little m. And so the force exerted at this point due to gravity is mg. The flower pot has mass capital M, so it provides a force of mg out at a distance from the wall of r sub m. We can find the torque provided by each of these two items right here, these two objects. And we need that because we're going to satisfy the condition of equilibrium by assuming that the sum of all the torques of these three forces add up to be 0. Now, to show you that we can actually use these distances here in our calculation, we should analyze the fact that if this is the point about which we're summing the torques, then each of these two forces will be located at a distance r, and remember that's r for each of these two. R is different for the two objects. But nonetheless, if I extend the line of action of the force, that line of action of the force, and r, you can see that the torque provided by each one of these would be equal to the force, and we probably ought to call that the force of, I'm just going to call it F. I'm not going to give it a subscript. Okay, I think that's confusing because this is Ft here. All right, so we have F, and so the torque provided by this force F is R times the force times the cosine of this angle, times the sine, I'm sorry, of this angle beta right here. But you'll notice that theta and beta are supplementary angles, therefore their sine is the same. Okay, so given all of the information, the R values and the masses, and the fact that we're trying to find this Ft, we can write for the two masses hanging out on the bracket, we can write their torques as the torque is the force of whichever one of these things you're looking at times its distance from the origin times the sine of beta, but the sine of beta and the sine of theta are the same. So I'm going to just rewrite it as the torque is going to be equal to the force times the distance times the sine of theta. But notice in each one of these cases that these R values that are given are equal to R times the sine of theta, so we can replace R sine theta with R. So here's how we're going to calculate the torque for the center of mass, the torque provided by the center of mass, and the torque provided by the object out on the pot out on the end of the bracket. Okay, so what we need to do now is to establish that we have equilibrium for this system. The sum of all the torques must be equal to 0. And so then we just need to put in the values for each of the torques. Now, the first torque that I'm going to calculate is due to this force right here. And you can see that that's the sine of the angle is 90 degrees for these. So the torque provided by this one is just Ft times RT. And since if I cross R into F, I'll get a vector that points out. I'm going to treat that as a positive, okay, since the torque will point out of the board right here, the surface of the board. The other two are going to produce torques that point into the board if you take the R's and rotate those into the F's. So the little, the center of mass then will provide a torque of its weight, mg, times its radius, its distance out, r sub m. And then likewise for the flower pot, which will have a weight of mg, okay, times, you multiply that times its distance out from the wall. And there's a minus sign again because that torque points into the board, and then those must be equal to 0. And then all you have to do from this point is just solve for Ft. Virtually everything is given in the problem, so it shouldn't be much of a problem to algebraically solve for Ft and then plug in the numbers.